Everyone, thank you for being back in the room. Just to remind you, we are now in a parallel session. So here in this room, we're going to talk about ISRU operations oxygen extraction from regolith. It will be moderated by Dennis Harries from ESRIC. And just in case you happen to be in the wrong room, the other parallel session will be in -2, the delegates room in this building with Larry Kujko, also from ESRIC, where you can find out more about the Pathfinder Challenge and the upcoming Space Resources Business Accelerator. But I don't want to take the time away from Dennis and the speakers. So with that, I will hand directly over to Dennis.
Thank you, Lisa. To this exciting session, I think, because we're going to talk about oxygen that's everywhere here, but very hard to get in space. So we have 7 speakers in this session, and we're going to look at how we can free the oxygen from the lunar rocks. And it's a tight session, and I would like to ask the speakers to look at the time, to stay about in a 12-minute frame, so that there is some time for at least one question for every talk. So the first one going to present is Timon Schild. He is a PhD candidate at ESRIC, and his presentation is entitled "The Characterization of Metals Produced by Molten Salt Electrolysis of Highland Regolith Simulants." Timon.
Hello, good morning everybody. So as introduced, I'm going to talk about molten salt electrolysis and especially about the metals obtained by this process when applied to Highland regolith simulants. So for a bit of context, this is a project conducted at ESRIC under an ESA co-sponsorship and also in partnership with Airbus Defence and Space. So the overarching objectives of the project, as you know, molten salt electrolysis, here the FFC process, can be used, that has already been shown in the literature, to produce oxygen and metallic remnants from regolith simulant. What we are now looking at specifically is those metal-rich solid products and how we can refine them further, first of all, into a feedstock that could then be used for additive manufacturing using Airbus's Metal 3D system that is currently being tested on the ISS. At the end, we hope to obtain 3D printed parts from that. And so our 2 objectives currently are, first of all, to characterize the metals we get from the process. This is what I'm going to talk to you about today. And secondly, demonstrate this process from lunar regolith simulant all the way to metallic parts. We did a series of electrolysis experiments using a setup very close to what has already been described in the literature. So just to go through it quickly, the regolith simulant we're using is LHS1 on one side, and we also did some tests with pure anorthosite, which is one of the constituents of LHS1. The regolith gets entered to a pellet that is introduced into a bath of molten calcium chloride. We apply then a fixed potential to this system, and the oxygen present in the regolith evolves through the salt and is released as, in this case, carbon monoxide and carbon dioxide at the carbon anode. This is how it looks in real life. And what we're really interested here is what we obtained afterwards, is this blob of solids that is left at the cathode in the basket. And this is what we're going to talk about now. So once this is recovered and cleaned up, we have this metallic-looking granular material. What we did with this for this analysis is, first of all, we sieved it into 5 different size fractions to see if this could maybe be used to separate the material further. We ground it to a fine powder for analysis. And then I'm going to present today 2 different analyses, 2 different data streams. First of all, we characterized the oxygen content that's remaining in those materials through inert gas fusion. And then we looked at the composition of the metals. The composition, we obtained it from SEM EDX. And we did analysis of some large areas that you can see depicted here that give us an average composition across the area. And then we also zoomed in a bit and did some point-by-point analysis of different particles. Going from here, so I'm going to go into the results. Being Catherine students, obviously I have a lot of graphs to go through. The first of all being this one, oxygen content of the products obtained for 4 experiments, 2 with LHS1 and 2 with an orthosite depicted here across the different size fractions. What we can see from that mostly is that most of the product is below, let's say, 4 weight % oxygen, with a slight increase on the smallest size fractions, so on the very fines. And then, knowing the amount of current we passed during the electrolysis, we can also calculate the current efficiency. And having used a similar setup to what has been done in the literature, we can compare. There have been some changes, but the experimental parameters and the duration of the reduction are the same, so for 24 hours. So over 24 hours, so the first thing we can see is that the process is applicable to Highland regolith simulants, which was expected, but it's always nice to confirm. And then looking a bit more at the numbers, we can see that the residual oxygen content is very low. So we extracted up to 99% of what was in there. And on the 24-hour period, that's actually quite a bit better than what was observed previously for MARE simulants. Again, the caveat, the setup is slightly different, but it still looks interesting, and we're at least as performant as the MARE counterpart, and probably more performant. Then the third point is we also see a higher current efficiency for the isolated anorthosite when compared to the LHS1 feedstock. We have about the same oxygen content, but the current we needed to obtain that was lower. Currently, based on this data, we don't really have a good explanation for it, because we can't really distinguish whether this has to do with the chemical composition or whether it has to do maybe with the sintering behavior of the materials themselves. But I think Beth later in the session will bring some additional data points to this question. And now, from now on, we're going to look at the metallurgy, so at what's actually in the product, at the composition. So this is the data we got from the average composition. You can see at the very top are the 2 feedstocks, LHS1 and an orthosite. And then moving down, we have the 5 size fractions, and for each size fraction, we depict the 4 experiments that were performed. Here, so the main metals in presence we can track are aluminium in blue, silicon in light green, calcium in dark green, and then the iron in orange. Then when we look at it from afar, first of all, we can see that if we move down across the size fractions, the composition is actually quite similar, or at least the variation between experiments is sometimes greater than the variation across size fractions. So the sieving of those products does not seem to be like a really useful approach, at least to enrich the material in a specific element. Next one, regarding at the iron content, as expected, we have higher iron, magnesium, and titanium with LHS1 feedstock, because in the isolated anorthosite, those elements are not present. Then, if we look at the overall iron in present, it is in all cases greater than what we have in the feedstock, and also we can see some exogenous elements appear. For example, we have chromium, manganese, nickel, etc. That indicates that we have some contamination that comes from the cathode, which is stainless steel. So it also shows us that there's still some progress to be done in terms of materials for the reactor. And then finally, this is a bit clearer on complementary analysis that is not discussed here today, but there is a negative correlation between the presence of iron and the presence of calcium in the product we're obtaining. So where you have a lot of calcium, you tend to have less iron, and vice versa. So this was what we had for the global composition, but now we want to look point by point what the actual particles, the actual product looks like. So this is what we did. Here we have, for all those points, we have a corresponding spectra and we have a corresponding composition, which gives us a slightly more complicated data set. So here we have about 1,300 points. And now to make sense a bit of that, we need to order it and coalesce it to a simpler data set. What we did for that is clustering, agglomerative clustering. So we ran an algorithm across it, and we reduced it down to 32 recurring compositions that here are ordered in order of side counts, of a number of appearances. Looking at that, so it's still, there's still a lot there, but I'll draw your attention to a few interesting things, mostly at the top, because that's what we saw the most. So first of all, we do have aluminium, silicon, calcium compounds with residual oxygen, and sometimes combined with magnesium. So that's expected if you're reducing something that's mostly plagioclase. Those are the components that you get there. Then we also have some more isolated aluminium silicon oxides that contain only residual traces of calcium. So the oxygen here is in gray, so those very high oxygen-bearing compounds. And then the iron compounds, as I say, don't contain a lot of calcium, but iron will combine with the silicon and the aluminium. They have very low residual oxygen, and then the presence of those stainless steel-derived elements. And finally, titanium, it's also quite interesting, always falls in the same quite narrow band of composition, which is aluminium, silicon, titanium, iron. So this is a very quite specific recurring composition. Looking at this, this sounds quite good, because we can see that we have some elements that are in higher presence. In one phase, for example, we have high iron areas, and then we have low iron areas. Maybe we could use this to separate it. Well, it's a bit more complicated than that. What we don't see here is the morphology of the particles. Here we're really just looking at points. If we look at the morphology, we can see that a lot of those phases actually occur simultaneously in one particle. So the example of this particle here, we can see 2 points we analyzed. Looking at the composition, we have an aluminium silicon calcium matrix with some inclusions of this titanium-rich compound we identified before. I'm going to plot those here now, and we can do this for a number of particles. So we connect them because they're in the same particle. Next particle I'm taking here will do the same thing, and I guess you can see where this is going. So here we have, again, this aluminium silicon calcium compound, this time combined with aluminium silicon iron, and also with a magnesium version of the initial compound. And if we do this across all the particles, we can kind of plot this graph of the of the compositions that are often recurring together in the same particle. And this kind of shows that even though we have some clearly distinct compounds, actually they tend to happen a lot together. And for example, the aluminium silicon side and the iron side actually tend to happen together in the same particle. Here, for example, on the iron-rich side, we can see some also some different phases: aluminium silicon plus iron or silicon chromium plus iron, which happen quite often together. And then a last one on the aluminium silicon calcium side. This is also something that happens quite a lot. We can actually see that we have some reduced silicon, so some quite pure silicon, and at the same time we also have some silicon dioxide. So it kind of is a good example of how complex this material still is. And what we want to take from this is that seeing the complexity of this morphology, it will be very difficult to separate just using physical means. So electrostatic separation, magnetic separation, sieving, etc., will most likely not be enough to separate this, especially because this has already been ground to quite a fine powder. So going even further will be difficult. So this brings me to my conclusion slides. The few points we found. First of all, the FFC process works quite well with Highland regolith simulants, which is always nice to know. We do have some material challenges that still need to be addressed. For example, the stainless steel in the cathode does tend to interact with the metals we are producing. We have higher current efficiency that we seem to observe for an orthosite, which is a good argument for prior beneficiation of the feedstock. We need to look a bit further into that to confirm this and also to find out why. And then finally, the complex morphology will make physical separation really challenging. So we will look into other processes, physical, thermal, chemical, thermal, etc. And then finally, what we're going with this, I just want to plug here quickly the new generation of FFC reactors that we're going to host at ESRIC. hopefully by the end of summer, and then we can start working with them and do some further experiments to address all the points mentioned before. Thank you very much for your attention.
Thank you, Timon. Other questions from the audience? Yes, I see many hands raised. I think Dorian was the first. Is there a microphone?
I have 2 questions, so I'll let you choose which one you want to do.
Go ahead.
The first one was, why did you choose anthracite? How would it look with other mineralogy? Then I think Airbus is also working on Roxy, which is, I believe, also FFC. So maybe you could mention how that collaboration looks. And you said 50% electron current efficiency. Where do the other electrons go? If you could explain something about the salt bath selection, and how do you detect the type of metals? So again, that's a lot of questions. You choose which one you think you'd like to do.
That's quite a few questions. Maybe I can quick fire through them. So we chose an orthosite because, first of all, the previous work had been done with Marway, so we wanted to confirm it with Highlands. And also from a programmatic aspect, Highlands at the lunar South Pole makes sense to see how this works. And there the main component is an orthosite. Moving on from that, yeah, you had quite a few questions there. Roxy, yeah. There's going to be a talk afterwards about Roxy, and we're not directly collaborating with this project for now, but it's definitely something we're looking into, because I think where you're going there, it would make sense to compare those 2 flavors of a very similar process. Salt selection, we made our life easy with the calcium chloride because we want to look at the metals, so we need to reduce them all the way. And so we're not really interested in the thermal efficiency, say, of the process. We really want to get all the way down to metals to see what we can obtain. Then the trade-off in terms of temperature, et cetera, will come further down the line. I mean, in the FFC process, it can be different things. It can be shuttling, for example, of the calcium, just the resistivity of the bath. You have a few different mechanisms that can happen there where you basically lose some of your energy. Also, just the system is heating in itself, et cetera, et cetera.
Okay. I see a lot of raised hands. Maybe you were first, then we have to move on to the next speaker because we're pretty tight.
Thank you very much. It's Jakub Ciążela from Polish Academy of Sciences. So my question is about the oxygen recovery. You said that from a fine-grained material, from the fine-grained fraction, you recovered more oxygen in absolute terms. And was that because of higher recovery rate or because of higher initial content of the oxygen?
No, this is not what we're saying, so sorry if this didn't really come across. What we did is we reduced the whole size fraction of the feedstock, and then we split it up and looked at the residual oxygen content in the different size fractions of the product. And so we can see that the product, the finest element of the product, contains still more oxygen. So that's the result we were seeing.
So you mean the residue in the residuum?
Yeah.
Okay, thank you.
So if you have further questions, I encourage to use the chat function on the website. So that's pretty good for this purpose. So we will change over. Thank you again, Timon. Thank you for the questions. So the next talk is also given by a member of ESRIC. This is Marko Sikiric, and he is also a candidate, or he's also working with the MRT LIST department on plasma. So his presentation is entitled Reduction of Oxides Using an Electron Cyclotron Wave Resonance Argon Hydrogen Plasma for Water Production. Marko, please.
Thank you, Dennis. Hi. I'm Marko, and I'm a PhD student at ESRIC, and on this project we're collaborating, as Dennis said, with Material Research Technologies Department of LIST, and we are going to look how we want to improve the currently proposed hydrogen reduction process, and this is also part of a PhD thesis. So this slide you probably recognize from the professional course on the space resources. It demonstrates the hydrogen-assisted gas reduction process. The idea of that process that we are directly producing water as we extract the oxygen, and it's a straightforward process, and it's also sustainable as we can reuse the hydrogen later as well. It uses moderate temperatures. It's not moderate enough to bake a pizza, but it's good enough what we can handle with materials. The challenge of the process is that it has a low yield, and it will rely on iron oxides so that we are also location dependent and dependent on beneficiation. So we want to propose to use plasma. And why do we want to use plasma? Well, when we look on the graph on the left, we can see activation energy requirement, or like a small barrier, and we have the black line and the red line. Black line represents the hydrogen reduction process with the gas, and we see that we need to cross that mountain to get to the metal and water, to our products. But if we use plasma, hydrogen plasma, we see that mountain becomes much easier to pass. So why plasma can do that? The hidden power of plasma is because it can create much more reactive species that are going to interact with the material. And the end goal of the project, the idea is to take these two processes and then compare them with Alchemist fluidized bed reactor from ESA, kindly lent to ESRIC, and it's currently situated at ESRIC laboratories. Ilmenite is a very popular choice for reduction with hydrogen, and it's favored because it has a simple chemistry, but also because of its iron oxide content. And we want to also take a more fundamental approach. We want to go from more simple to more complex process so that we understand what's going on with the reduction process as well. So we are going to start with the iron oxide part, and we're also going to start with the thin films. This is going to enable us to have a lot of characterization techniques available and to follow the process, how it behaves. To do that, basically we have two machines that we use. We have on the left, we have a physical vapor deposition machine. Its job is to produce iron oxide thin films, which it successfully did, Fe2O3 phase, and then we use this thin film and then we reduce it with a novel proposed plasma source with low temperature plasma as well to save power. And this is how we treat in this chamber on the right. First things first, we wanted to compare the efficiency of these two processes preliminarily in our chamber. So we filled the chamber with the hydrogen-argon gas mixture on the left, and we heated the sample at 700 degrees, and we collected the weight loss of the sample after that, and we repeated the same process, but in this case we did not use any heating. We only utilized the same gas pressure with plasma, and then we compared the processes. This gave us a metric to compare it. So we obtained how much of energy we use to extract 1 microgram of oxygen per centimeter square. When we put the numbers together, we get that plasma, in our case, in this preliminary investigation, is using 6 times less energy than a gas reduction process to extract 1 microgram of oxygen per centimeter square. We're going to dive in a little bit into graphs. So on the left, we are looking on the XRD with varying grazing incidence angle. It's a sample that has been treated for only 15 minutes with hydrogen plasma. We're focused on the black line spectrum, and we see that we have a peak of metallic iron, and we also know that plasma during that time naturally heated the sample up to 56 degrees, which indicates that we are able to, on the very surface layer, reduce the Fe2O3 down to the metallic iron at only 56 degrees. We went further and we performed some SIMS depth profiling of the material. On the left, what we are seeing is basically the oxygen over iron ratio of samples, various samples that have been reduced at various times with hydrogen plasma. but it's more useful if you refer to the right part, which showcases the model that comes from it. What we learned from the previous slide and this one about this, with this characterization technique, is that the reduction process occurs very fast at low temperatures, and we have formation of metallic iron, but the reduction process will then slow down. And the interesting part is that we are going to start, as the time goes by, forming a very specific intermediate layer of a composition. So this kind of fundamental investigations help us to understand the process and maybe can give us insight how the oxygen or water is being transported from the material into the environment. With that, it can also help us scale and improve the process, hopefully, in the future. Now let's get more visual. So how does material look before and after the reduction with hydrogen plasma? On left, we have the reference sample. It's a cross-section. It's a SEM image. And we see classical columnar growth. We see these columns of Fe2O3, of iron oxide. And as we can see on the right, as soon as we treat the sample, in this case, we also used the heating as well of the material, and we reduced it with hydrogen plasma for 2 hours. We can see very strong indication of morphological change. We see formation of porosity. We see the formation of these columns as well, and also grains appearing. We wanted to compare the processes as well, hydrogen and gas process at the same temperature. In this case, we see that the red line and the black line spectrum, they look basically the same. It is not visible on here on this graph because they are stacked, but there is some extraction of oxygen occurring, but there is we cannot see any phase transformation. But if we look at hydrogen plasma treated sample, which is the blue line spectrum, we see only one peak, and that peak belongs to metallic iron. Since we looked through all of the material with this with XRD measurements that we performed here, we concluded that we extracted almost all of the oxygen from 0.5 micron of the material of iron oxide at 700 degrees. But let's go away from the graphs and see how it looks more visually to confirm it. On the left side, scenario with the hydrogen gas reduction, and on the right we have the plasma reduction where the material is treated at 700 degrees. We can see on the left side that there is some merger of columns and some slight indication of morphological change, but the story is completely different on the right side, as we see that we have these coalescing islands, these stone-like features. What is left actually is this metallic iron that is trying to coalesce into a layer of metallic iron. And basically, when you look at these differences in the thicknesses or the heights between the left and the right image, this basically tells you that all of that oxygen from the left, how it looks when it's extracted. Lastly, what we wanted to do is we wanted to also preliminarily test, can we go beyond the iron oxide with hydrogen plasma with our setup, because this is one of the limitations of the gas reduction, hydrogen gas reduction process. And we performed some preliminary investigation with that and reduced it 600 degrees. Black line spectrum, Raman spectrum, we see titanium dioxide in film, anatase crystal phase in this case. And after the treatment, we can see that we have new peaks appearing, and these peaks belong to dititanium trioxide. The interesting part is that dititanium trioxide phase is the less oxygenated phase of titanium dioxide, so this indicates that we do indeed extract and are able to extract oxygen from titanium dioxide. This tells us about the potential of the plasma to tackle the challenge of the location or to go even beyond the iron oxide part of the ilmenite and regolith in the future as well. With that, I will just shortly conclude what we saw. And what we did in this presentation, we wanted to improve the hydrogen reduction process. We proposed plasma. In our case, we proposed the low temperature novel type of source to perform its job. And we measured the energy efficiency between these two processes preliminarily, and we concluded that the plasma is more energetically efficient. We saw that we have a formation of metallic iron at very low temperature of 56 degrees. And then we also observed this model and a very specific intermediate layer forming, which can give us an indication of the mechanism process as well. This is ongoing research as well. And then we visually confirmed how does that actually looks when we zoom in and look through the microscope. Lastly, we compared and we wanted to see can we go beyond iron oxide with our setup and hydrogen plasma, which indeed we can, and with that it shows the potential to go beyond and reduce other parts of the minerals as well. With that, I would like to conclude and say that with this, I hope that you also now believe more that the hydrogen plasma process is the way forward for the hydrogen reduction process for the sustainable ISRU on the moon and beyond. Thank you.
Thank you, Marko. Other questions? Jerry.
Okay, so to be clear, in your research, you created the iron oxide first, and then you reduced it. So you didn't take a mineral like ilmenite and do that yet. Is that correct?
Yes, that is correct. So the idea behind it is mentioned in one of the slides. Because this is also part of a PhD project, and we wanted to first study the fundamentally how the process occurs. So we are building from the more simple process to the more complex process. Of course, later we are going to assess the minerals and the simulants, but we first want to see how the reduction process occurs, so that occurs with our novel proposed plasma source. And then we want to move forward and try to optimize it as well, and to maybe also try to better scale the process. Yeah.
Yes. Yes, thank you, Mark, very much. Maybe I missed it or was not. So what is the pressure inside your chamber?
So the base pressure that yes, I did not mention, thank you for the question. The base pressure is 10 to the minus 8 millibar, and during the reduction process, we have, with the gas mixture of 90% hydrogen argon, we have around 10 to the minus 3 range of the pressure of millibar.
Yes, Robert.
So thank you very much for the presentation. From what I've seen, this process is pretty much diffusion controlled.
Yes.
To the layer. And have you somehow tried to evaluate what is the sweet spot between, let's say, residence time and then yield, where you say, okay, until here, I mean, you showed the one graph, until here I get really good value for money, so to speak,
yeah.
And I'd rather stop instead of investing even more energy in trying to get the last amount of oxygen out of it. So kind of process optimization.
Are you referring to the part where we had the reduction to the metallic iron part? Or?
Yeah.
Okay, so as you said, it's a diffusion-related process, and after 2 hours, we are going to have this metallic iron formation layer on top, which is going to be very thin. That layer will become very stubborn. So this is without any material heating. It will become very stubborn, and what happens is in that model that was shown. Oh, sorry, I went to another presentation. I was thinking that mine is still on. In the model, it was and when we did the seams depth profiling. So the metallic iron layer becomes very stubborn, and it seems to be the same thickness, while the intermediate layer forms a very specific composition. This is what I'm still trying to investigate, to give us some clue with TEM to maybe understand how the oxygen or water is being transported. So the process slows down, and if we want to propagate the reaction rate, we actually need to heat the material.
Okay. Can you derive maybe requirements for the beneficiation, say particle size, which is optimum in this respect?
So,
most efficient processing?
in this sense, we managed in two hours, so we reduced half a micron of iron oxide. It's tough to really say what would happen, as Jerry kindly pointed, that what would happen when we would actually switch and try to relate it to the particle side. For now, I don't have a proper answer for that. Thank you.
Okay. Thanks a lot for these great questions. I don't want to quench the discussion, but we have to move on. So thanks again, Marko.
Thanks.
And our next speaker is Georg Poehle from Fraunhofer IFAM. And his talk, and he will actually talk about Roxy, Mini Roxy towards a lunar demonstrator for oxygen and metals extraction from regolith. Please.
Thank you very much, and it's great to be here. Good late morning to all of you. We have already heard a question about Roxy. Unfortunately, I won't be going into the same level of fascinating detail as my previous speakers, but I'm trying to give more of a general overview of what we're doing at the moment, where we want to go, and what our goals are. This is a team effort. As you can see, this involves people from Fraunhofer IFAM in Dresden, where I am from, Airbus Defence and Space, TU Freiburg, and also Boston University. So, as a short outline, my early remarks on ISRU viability and scaling will be very brief, because you all know this very well, and we've talked a lot about this in the past 2.5 days. I will then give a short update on the regolith to oxygen and metals conversion, or Roxy process, and Mini Roxy as its younger cousin. I will talk about where we are with this development and where we want to go, namely the preparation of a lunar demonstration mission. And finally, I will also say a few words about possible scientific collaborations. So first of all, the promise of ISRU is minimized upload for affordable exploration. And to do this, we need facilities with a low mass and high efficiency so that we can reach a break-even point between the initially uploaded mass of the facility and consumables to the materials which we have produced in situ and do not need to upload anymore. We also want low complexity facilities with a minimal need for consumables and spare parts. And of course, we want scalability, because on a timescale of decades, we will need to expand by several orders of magnitude, or otherwise sustainable exploration will simply not happen. So the Roxy, or regolith to oxygen metals conversion process, is a molten salt electrolysis, which was specifically conceived for the extraction of oxygen from lunar regolith. It is based on 3 key components, the first of which is the solid oxide membrane type anode, which you can see on the left-hand side of the schematic. In this type of anode, the anode is a metallic material, but it is separated from the reactor and the electrolyte by a zirconia membrane. This zirconia membrane is a highly efficient or highly selective oxygen ion conductor, but is not an electronic conductor or conductor of any other ions. This means that it can act as a very selective gas purification system, which is built into the reactor. And it also means that we do not need a separate gas purification or separation system. The second important component is the porous metal cathode, which you can see on the left-hand side. This is an open porous metal structure, which is mostly in the responsibility of IFAM. And this is working on the one hand for the regolith containment during the process, and also the retrieval of the reduced material after the electrolysis is finished. And finally, we also have the eutectic fluoride salt mixture, which is made for processing at 850 to 1000 degrees Celsius, and which was developed to be compatible with a zirconia membrane. All in all, we have a process which works at a relatively moderate temperatures when it comes to material compatibility. It is a relatively simple process. And it is also quite efficient because a secondary function of the zirconia membrane can be to block parasitic electronic currents in the system. Mini-Roxy represents a further simplification and miniaturization of this process to provide something of a minimum viable demonstration. As you can see in the image on the bottom, the main difference to the original Roxy process is that the reactor vessel is removed and the zirconia membrane now also acts as a reactor vessel. This has some advantages in material compatibility, but also significantly reduces the size and the mass of the system. And it means that in a relatively lightweight so-called cartridge, which is shown on the right-hand side, we can perform the reduction and the extraction of oxygen. You might wonder why we want to go smaller when scalability or larger scales are actually the end goal. But the idea here is to create a relatively small and simple system for an initial demonstration, which can then be scaled up. And Mini-Roxy is also suitable for this purpose because on the one hand, the cartridges can be scaled, and on the other hand, they can also be used in a modular system where you can use them as repeating units in a larger facility, which would also mean that you don't have a concentrated single point of failure in one large facility. So Mini-Roxy itself was invented or conceived in 2021, and the first 18 months or so, aside the Roxy development, were mostly early development and figuring out a viable design. We did some initial performance checks, so we checked whether the components we had in mind were suitable for the extraction of oxygen and the amount we envisioned this. We tackled some key technical issues in breadboard testing, such as regolith retention and the redesigned cathode, system resistances, and also the sealing concept. We also did a theoretical lunar environment assessment, so checking things like vacuum compatibility, thinking about the influence of gravity or lunar dust. And we created a first very rough design. This was just very bare bones to give us an idea of where we would like to go with weight, dimensions, power budget, and so on. And since September of last year, we were able to take this to the next step. This is thanks to a grant from the German Space Agency with funds from the German Ministry for Economic Action and Climate Affairs, which I hereby want to gratefully acknowledge. In this project, which is called Ground Testing Campaign in Preparation of a Lunar ISRU Demonstration, we will build a lab model which is dedicated to this specific process and use it for a ground testing campaign. The lab model is currently under construction and will hopefully be available in the second half of 2024 for the first test campaign. In this test campaign, we want to build detailed process knowledge, and we want to demonstrate reproducible oxygen extraction from regular simulant in this dedicated model. While we do this, we also want to investigate the extraction of metals and alloys and the analysis of their composition and morphology. And finally, one important part of this project is also to provide a mission concept and a design for a lunar demonstrator. So this slide shows some of our initial thinking about the mission concept. This is of course not set in stone because we do not have a specific flight opportunity, but it's, let's say it's the general range in which we want to work. The mission objective, as already mentioned, is to produce oxygen in a very small volume of around the equivalent of 1 liter at standard pressure of oxygen in much less than 1 lunar day. And while we do this, we also want to analyze and understand regolith properties and their influence on the process capabilities and limitations in a lunar environment, and of course the products. This is supposed to be a robotic mission in which Mini-Roxy can present a secondary payload on a commercial lander. There are some interfaces where we will need an external system. I'll talk a bit more about this on the next slide. So this shows a general overview of the steps you have to go for this demo, and you can see on the left-hand side in blue are the steps which would be predestined for an external system. And this is excavation and delivery of regolith, steps of beneficiation if needed, and also the delivery of the regolith to the Mini-Roxy inlet. So this is where we would like to interface with an external system. But the Mini-Roxy demonstrator would be designed in a way to pose as few requirements or hard requirements to the external system and be as tolerant in this respect as possible. Once the regolith has been delivered, the core functions of the demonstrator would kick in, which would be the transfer of the regolith within the system into the cartridges, pre-processing and extraction of oxygen, the built-in separation and purification of the oxygen, and of course, process and product analysis. When it comes to the design, the current project has two design phases, the first of which is almost finished. And you can see the result of the design in a few images on the right-hand side. The current design consists of the reactor subsystem, 3 cartridges, the control and the power subsystem, and the support structure. This is shown on in the top image without any thermal isolation layers. And you can see the 3 cartridges in the center of the demonstrator. Because the cartridges are more or less the critical element of the entire mission, we have introduced some redundancy here, and we have 3 cartridges, but they are identical in design, in function, and in operation. The objective was to go to a suitable size and mass as a secondary payload. And one of the main challenges was consequently that we had to balance between the mass, between the mechanical strength and stiffness requirements, and also the thermal bridges in the system, which needs to be heated to around 850 degrees Celsius. But in the end, we figured out a design which has a total mass budget of slightly less than 30 kilograms, including the margins, and which also works from a mechanical and thermal standpoint. The whole thing can be seen in the lower image with the thermal isolation layers, and it has a diameter of around 50 centimeters and a height of around 30 centimeters. The maximum power draw for this would be far below 150 watts, under the assumption that we need to heat to 850 degrees Celsius, and then hold this temperature during processing for at least 10 hours. And finally, some words on scientific collaboration. We all know that one small team cannot cover all the topics which are needed to make an ISRU mission and demonstrator a success, because we need beneficiation, we need understandings of rheology, diagnostics of materials, the process and the electrolyte, and also metallurgy. And this is why we're always interested in talking to more parties about scientific collaboration for a future demo mission. We have assembled a lot of the info I've talked about now in a document, which you can find on the homepage. And if you're interested in this, please take a look. And with this, I'm at the end of my talk. Thanks for your attention. And if there are any questions, I'm glad to answer.
Thank you, Georg. Other questions? Yes, Alexandra.
Thank you, Alexander Meurice, Neamine. Thank you for the presentation. What yield did you achieve so far with your eutectic fluoride mixture, salt mixture?
Excuse me?
What recovery of oxygen did you achieve so far?
In some early experiments, we were at around 85%. This was an early installment of the process, and we can already see that there were some problems, for example, with material compatibility and some leaking in the system, so we hope that we can improve this further.
Yes, Dorian?
Thank you for the very nice talk. I was just wondering, in this early concept for the lander system that you showed, do you envision that you would store the oxygen that you produce or just release it to the lunar environment?
In this first iteration, we just thought about producing the oxygen and then releasing it, with this idea of having the entire system very simple. But as I said, this is not set in stone, and if we see that it can be a requirement from, for example, external parties that we want to store this oxygen for later analysis, then this can also be added to the system.
Thanks. And maybe just another quick follow-up question. In terms of the power draw, you said 150 watts?
Less than that, yeah.
Less than that, yeah. Do you know approximately how much is used for heating up the regolith versus running a current at whatever voltage you're using? I think 3.2.
Yeah. Well, the heating power is actually the largest part of this. In the last model which we had, it was around slightly below 80 watts, so about half of that. So a lot of this, of course, has to go into the heating of the entire system, and then the electrolysis itself isn't that much of a power draw in comparison.
So I think we have to move on to the next talk. And thank you, Georg, again.
Thank you.
And the next talk will be by Sean Kelly from Dublin City University. And his talk also concerns something with fluorine, fluorinated plasma-based oxygen extraction from lunar regolith. Thank you.
So, good morning, I'm Sean. Just to acknowledge our collaborators in European Astronaut Centre and also Durham University. So I'm based at DCU in Dublin. So the idea here is to take some inspiration from semiconductor fabrication processes. So these regularly remove oxides and dielectrics, where plasma is the key enabling technology. Low temperature plasmas, as we heard earlier, have unique characteristics. They enable a high temperature chemistry at effectively low gas temperatures. And this has to do with electrons. They can be preferentially heated. They have low mass compared to the other species in the discharge. Also, they favor vacuum operation, so they're conducive to lunar conditions. So typically halogen chemistries and fluorocarbon gases are used, some containing sulfur, some like C4F8, which we'll discuss in a moment. And these are typically employed to etch chemistries like silicon dioxide. So the hypothesis, and this is a very exploratory work, is could a fluorine-based plasma be useful for oxygen extraction from regolith? So just to acknowledge the funding here is from an OSIP study to DCU. So here on the right-hand side is a graphic from a schema for a closed fluorine system for regolith treatment from one of our collaborators, Aidan Cowley. In this schema, KF is used to recycle the fluorine, and it involves several steps. One of the steps actually involves a plasma for the liberated silicon tetrafluoride for producing solar arrays. The potassium is used to reduce the regolith after the fluorination. So really, we're not proposing a schema here. We're just exploring the idea of if the plasma could be useful inside the fluorination reactor. So here's our setup. It's a capacitively coupled parallel plate plasma reactor from Oxford Instruments. It has two electrodes, a top electrode which is powered, and a bottom electrode separated at about 3 centimeters, which has a heated grounded electrode. It's driven at about 13 megahertz. The plasma is formed inside the gap at pressures of typically less than 1 torr. We are focusing for this study just on the gas analysis of oxygen, carbon monoxide, and carbon dioxide. So on the right-hand side here, you can see inside the reactor chamber with the lid pulled up. And we can see the regolith is placed, loose regolith is placed about 10 grams on the heated grounded electrode. We're using 2 gases which are available to us, one with sulfur and another fluorocarbon gas. So just a note on the regolith that was used, we've used the LMS1 simulant. So this has 5 basic mineral components. In terms of looking at what the plasma is going to do, silicon dioxide is the most abundant oxide, so I'll use this as a kind of approximation of the chemistry going on. So here is an operational video of our setup. So hopefully this works. Yeah. So the camera is zooming in and out and just showing you what we would see when we're looking at the viewport. So you can see the glow. It's quite wide, about 20 centimeters. And a depth of 3 centimeters. And the regolith is placed on the grounded electrode. So here's the first gas that we treated our regolith with, and this is SF6. First of all, on the left-hand side, just to say the conditions that were used, these are typical for this reactor. We're using about 10 skims of mass flow, power of the order 200 watts, pressures of around 0.2 torr. In order to get an idea of the metrics involved of the energy, of course this is not optimized, it's just an exploratory study. I've calculated the specific energy input. So it's the order of 50 watt-hours per gram of gas, and we're only flowing about 4 grams of gas per hour of SF6. So on the right here, we can see some of the production values. We've analyzed 3 gases. There's no carbon source in there, so we're not seeing any carbon production or CO or CO2 production. We're only seeing oxygen production. And we've varied the heated plate temperature. So 30 degrees here represents ambient, no heated plate on. 200 and 400 are set points for the heated plate. So indeed, we do need some kind of heating on the plate to get the reaction going. But once it's going, we're getting somewhere around 2 to 5% of the exhaust mix that has oxygen in it. This is a production rate which is quite small given the flows of about 50 milligrams per hour. Looking at the energy cost, it's the order of 4 kilowatt hours per gram. So taking that energy cost and comparing with the specific energy that's input, I can get an idea of the efficiency for this kind of conversion. And of course, this is not optimized. There's a lot of wasted volume in the plasma, for instance. But the efficiency is around 1% for this. Now, SF6 is much more stable, and that's its benefit. That's why it's being used than fluorine gas. So we'd expect these kind of values. So the second chemistry is a fluorocarbon chemistry. The gas we've used that was available to us is C4F8. For this, we have the same conditions for mass flow and power, similar ones for pressure, and our specific energy is slightly different due to the molecular weights. So it's about 40 watt-hours per gram. What we see first in the graph is that we don't have any oxygen production. It's all carbon monoxide and carbon dioxide. We also see that the heated plate is playing a role in increasing the yield, but it is not necessary to have it. The ambient temperature within the reactor is enough, actually, enough to allow the carbon dioxide and carbon monoxide production. In terms of absolute values, we're measuring about 10 to 25% of the CO and CO2 in the exhaust. Production rates in terms of absolute values are about 0.5 gram per hour. So if we combine those two together, we can get an estimation of the energy cost. It's about 0.5 kilowatt hour per gram. So this is an order of magnitude increase over the SF6. Then looking at the specific energy and the combined energy cost, you can get an idea of efficiency. It's about 9%, so again, an order of magnitude increase. So we've also been able to do very preliminary surface analysis of the regolith to get an idea of its changes in its composition. This was carried out by Beth Lomax, I think at ESRIC, not EAC. So she did some XPS spectroscopy to look at the surface composition after C4F8 plasma, the fluorocarbon plasma treatment. And what we're seeing generally is that the oxygen is being depleted as expected. The silicon is also depleted, and that's because it's a volatile. Fluorine and carbon are being added to the surface also. We've began to do some surface analysis also at DCU for SF6 chemistry. We're seeing a similar trend, of course, without the carbon, because there's no carbon source. So we're also looking to analyze the crystal structure with our collaborator in the University of Durham, Brian Tanner. Brian has taken the XRD profile for the main mineral components of interest, anorthosite, bronzite, and olivine. And he's used this to baseline the XRD profile for the LMS1 regolith. And then he's been looking at the changes only recently to do with the plasma. So he's seeing that the changes are mainly associated with the anorthosite peaks, but we don't have much more insight other than that at the moment. So investigations are ongoing into that. So this is a penultimate slide of content, just to kind of give some insight into what we think is going on in terms of the chemistry. On the left-hand side is the oxide component of the regolith that we're using. The expected fluoride salts, of course, silicon tetrafluoride, SiF4, is volatile, and also this fluorine is going to be deposited to supplement the oxygen in the regolith itself. So in terms of the SF6 plasma that we've shown, we expect that the mechanism is quite similar to a thermal fluorination, and indeed with the heated plate we may have some of that going on, in that the atomic fluorine is interacting with the oxides to abstract the oxygen. For the fluorocarbon chemistry, we're seeing it's typically a polymer promoting chemistry, so I can actually see some evidence of thin films formation inside the reactor. So this is actually exploited, maybe not so well understood, but it's definitely exploited to get very high selectivity of silicon dioxide over silicon in the industry. What's happening is the thin film is being created and destroyed continuously, and the carbon inside the tin film is reacting with the oxygen inside the silicon. So it's not very complete in terms of the understanding of that, but it's certainly being exploited. So in summary, we hope this shows that plasma-based fluorination shows potential, at least for lowering the operating temperature and allowing gases, such as we've shown, which are much easier to handle than fluorine gas. You may have more complexity, but it is quite a complex schema already. What we found in summary is that at the sulfur-containing plasma, the SF6, produces O2 directly. The fluorocarbon gas, C4F8, produces CO and CO2 without oxygen. We also saw that we didn't need to heat the plate where the regolith was with the C4F8 plasma, so it can do this at room temperature. The mechanism for SF6 appears to be analogous to thermal fluorination, while the C4F8 is giving a novel mechanism involving thin film formation. So, yeah, thanks for your time. Cheers.
Thank you. Other questions? Alberto.
Do you have any correlation of the plasma density with the extraction yield of the process?
The density of the actual charged species would be much lower than the percentage of oxygen or CO2. It's typically 10 to the 4, 10 to the 5 orders lower. So the plasma itself, in terms of the charged species, is much lower, typically, than the neutral species that aren't charged. So you have a relatively low population of electrons that's driving the whole chemistry, but it's much less than the the oxygen or the CO or CO2 produced. That's usually, but no, we don't have direct measurement.
Another quick question? Okay, then I would say we move on. Thanks again. So, until now we've looked at using simulants in the lab. Now we are actually taking the moon to the lab. So next up is Beth Lomax from ESA, and she's going to talk about the extraction of oxygen and metals from real Apollo regolith using molten salt electrolysis. Please.
Thanks very much for the introduction. I'm Beth from ESA, and today I'm going to talk about the extraction of oxygen from Apollo samples using molten salt electrolysis. So I'm presenting this work on behalf of a team in the lab, Dina, Alex, and Arno. It wouldn't have been possible without their support. So I probably don't need to go into this given the previous talks in the session, but just very briefly, molten salt electrolysis, or also known as the FFC process, is in a bath of calcium chloride salt. The regolith is going in at the cathode in the solid state, and in this process we can use a carbon anode or an inert anode if we're looking to target oxygen directly. So it's been shown to work reasonably well with a simulant material where we can remove almost all of the oxygen, but of course that leads to the key question is does the process work with real lunar regolith? We also wanted to address the question of how do the regolith feedstock properties impact the reduction behaviour, because obviously the moon is not a homogeneous body, and also how does the reduction of real material compare to the simulant material behaviour. So onto the samples that we used as a feedstock. We were lucky enough to be allocated 4 Apollo samples, 1 gram per sample. And so we got 2 Mare materials, Apollo 15 and Apollo 11, and 2 Highland materials. So for each category, we requested an immature and a mature sample. So to just quickly go into those terms, Mare versus Highland. So Mare material is the darker parts on the lunar surface. It's basaltic lava flows that have filled the impact basins, primarily on the near side. The highlands material is the lighter, older, and orthositic crust. So they just have slightly different chemical compositions, as you've seen in lots of previous talks. Mature versus immature. So here the maturity just means that the material's been on the surface of the moon, exposed to space weathering processes for longer, so more micrometeoroid bombardment. So that means there's a lower average particle size, more glassy agglutinates, and more nanophase iron. So for each of these samples, we split them into two portions, kind of A and B, to try and get at least one repeat from this quite small quantity of material. And the simulants that we used for the study to compare were the LMS1 and LHS1 simulants from Exolith Labs. So the first thing we wanted to do was measure the oxygen content. Of course, if we want to understand how the oxygen extraction processes worked, we need to know how much oxygen we have to begin with. So the Highland material, the Apollo 16 material, had roughly 44% weight oxygen, and this was very similar to the Highland simulant material, also around 44%. However, for the Mare material, we got quite a different result. It's about 10% less oxygen available in that material. The Apollo 15 and Apollo 11 both had around 38% weight oxygen, compared to the Mare simulant material that had closer to 42%. And so this is kind of reflective of the really unique environment on the lunar surface, where that material that has a really high iron content, like the Mare material, is going to be in a much more reduced state because of that micrometeoroid bombardment, so with that nanophase iron being present. So you can see here the dark bars on this chart is the kind of predicted value that you would get from the stoichiometry. And we can see that for the Mare material particularly, and also a little bit for the Highland mature material, we get a lower measured content, so we've got less oxygen available in that material. So onto the experiment method. We first sintered the material, the powdered Apollo samples, into small pellets. So this was primarily to not lose it in the salt if we'd left it in the powdered state, to try and make a really cohesive block. We then produced these kind of small electrodes. The Apollo sample you can see is inside that tiny metal basket. We cycled through a range of different options for this kind of miniaturized basket. And what we settled on was not necessarily the most efficient, but it was the best balance between efficiency and protecting the material, because the thing we were trying to avoid mainly was losing the material before the reduction had actually taken place. For this experiment, we chose to use carbon anodes. This was primarily because the main goal of the experiment was to compare the behavior of the material at the cathode, the actual samples. And so the carbon anodes allowed us to have a off-the-shelf, very consistent anode. And also we weren't producing oxygen directly, which is often lost in the reactor onto the metal surfaces. So it allowed better comparability. So for the molten salt electrolysis, we did this in molten calcium chloride. We found that the process was quite sensitive at the miniature scale, much more than at the large scale. And we chose to use some quite gentle parameters, so only 2.8 volts, and we ran for quite a long period of time. I think it's important to highlight that the duration does not scale linearly, so the time per gram at a larger scale is going to be much, much lower than what we got at this miniature scale. And then for the gas that came out, we went through a coarse and fine filtration, analysed that by mass spec. And for the solid material, we washed the salt off, crushed it up, and then dried, weighed, and analysed it. So to start with the first question, does the process work with real lunar regolith? The short answer is yes, which is great. So this graph shows the extraction based on the gas data, and then also the extraction based on the solid material analysis, so looking at the oxygen that was still residual in that solid material. So what we can see is there's a bit of a discrepancy between those data points. So for the first run of each sample, for sample A, we ran to around 100% gas extraction. However, we do have other oxygen sources within the experiment. So here you can see the alumina sheath that's on the rod of the cathode. This was necessary in such a tiny system to avoid any short-circuiting between the rods. But yeah, that was another source of oxygen in the system. So for the second experiment, we ran a bit past 100%, with the delta determining how far we overran on the second run. And here we got the 2 Highland samples down to around 3 and 4 weight% oxygen, respectively. So that equates to over 95% oxygen extraction corroborated between the gas data and the solid product analysis. So from that we can say that the process does work with real material. However, we can see that clearly there's the difference between the Highland and the Mare behaviour. With the Mare material, the red and the yellow spots there, we never got above 80% extraction, and even when overrunning the process a lot the second time round, we didn't really get much beyond, so the process had kind of stalled. So that leads to the second question, is how do the regular feedstock properties impact the reduction behaviour? So here we can really see the difference between the Mare material and the Highlands material, where for the maximum extraction we got was 78% as opposed to 99%. The minimum oxygen content achieved in the solid material was much higher. The average current efficiency was about 10% lower across the entire experiment duration. And also when looking at the peak of the current efficiency that was achieved throughout the experiment, that was around the same, 55% for each of the type, averaged across all 4 of the runs. However, for the Mare material, this occurred much earlier in the experiment. And so it means that for the Highlands material, we can get a lot more oxygen out before the efficiency drops way off at the end. So overall, under the conditions that were chosen, the process worked better with Highlands material compared to Mare material. The soil maturity, so the average particle size, had less influence than we were expecting, actually. It influenced the reduction onset right at the beginning, but didn't have much of an impact on the overall reduction behaviour. The material also behaved quite differently when it was in the reduced state. So for the Mare material, it remained very solid. Only a couple of particles were fused to the basket, whereas the Highland material was kind of really sort of formed a soft molten blob, some of the material onto the basket. So there was a much greater discrepancy between the total material recovered compared to the material recovered as a powder. For the Mare, overall, we recovered less because the material was always in that powdered form, so more of it entered the salt and was recovered separately from the starter. So then looking at how the reduction compares to the simulant material, which is important to understand how we can use those simulants in the lab to optimize the process. So the Apollo Highland material was very similar to the LHS1 simulant, but the Mare material was quite different to LMS1 simulant. And putting those onto one chart, you can see that the LMS simulant behaves more like the Highland material for the simulant and the Apollo samples. So the outlier is really the Apollo Mare material here. And that's not to say that we didn't see any difference between the 2 simulant types, the same as Timon was presenting earlier. We in general see that the Highland material does reduce better than the Mare material, so 98 versus 90. But this discrepancy becomes much larger when we look at the results from the Apollo samples. So the Mare material, as I said, never got above 80%. So that leads to the question of why. We don't have a really defined answer yet from this data set. But it appears to be related to the fact that the Mare material forms this kind of metallic outer shell, and then it really blocks access to the interior material. It's kind of hard to see from the picture there, but it was easier to see when processing the material visually. There was this really kind of outside core and then an unreduced inner core. And so that might be relating to the compositional differences between the materials. So how much calcium is being uptaken and forming intermediates, and maybe that volume expansion is blocking pores. It may also be related to the fact that the Apollo Mare material is a lot more nanophase iron, so that could be acting like a susceptor in the material and really rapidly metallizing the surface and then blocking it that way. It also could be related to the fact that the material behaves differently once it's in the reduced state, with the Mare material remaining fused and blocking access a bit more than the Highland material that was falling away. So we're still kind of working on trying to understand that. And so I wanted to present this work as well. It's ongoing at the moment. Alex is working on the metal analysis. He's collecting a huge number of spots per reduced sample and then doing a clustering analysis similar to what you saw earlier in Timon's presentation. So I don't have time to go into this in detail, but the main point I just wanted to highlight is that from the analysis we've done so far, it seems like the same alloy groupings are formed in the Apollo samples compared to the simulants that are being reduced. So that's promising in terms of using those simulant materials for extracting metals and understanding that process. So just to conclude, I wanted to show some pretty pictures. So the Apollo 16 sample there, you can see the metal powder, and then that's a close-up of some of those metallic grains. So that material has around 3% oxygen in it, which in terms of ISRU is pretty low in oxygen in terms of the metal world. That's terrible, but we'll take it. So the main takeaway from this is that molten salt electrolysis works with real lunar regolith, which is really promising. It's shown that we can extract oxygen and produce metals in situ on the lunar surface. The results highlight that from what we know so far, highland regolith seems like it would be a preferred feedstock, which is quite positive given the likely landing locations at the polar regions. And yeah, analysis is ongoing to understand the solid metallic product more. We're doing a lot of SEM, EDX and XRD analysis, and we're still trying to understand the reduction behavior that we've seen, but it's likely that more experiments would be needed in the future with a wider range of materials and different parameters to really dig into the differences that we've seen. And yeah, finally, of course, plenty of development is required to make the process space ready. But yeah, thank you very much.
Thank you, Beth. Other questions? Yes, Carl.
Carl Hibbett, CPL. Beth, great talk and really great results, really interesting. Question about scaling up. What would have to be changed, modified, or done differently if scaling up to more what we want for a pilot plant on the moon?
Yeah, that's a really good question. There's a lot of various activities that are looking into this specifically. So my view is that I think it would be really beneficial to remove the sintering aspect entirely. Having a process that was powder in, powder out would be ideal, but obviously it's extremely hard to contain such a fine powder inside the reactor. And you've got the issue of if you're trying to contain it with a mesh, the finer the mesh, the less likely it is to survive in this quite corrosive high temperature environment. So at that point, I think the work that Alexander Rutzler has presented outside on a poster is really important. He was looking at the liquid cathode concept, where you could really just pour the powder in and then possibly tap the metal out. And I think going in that direction would be really interesting if we can get that to work.
There was another question in the back. A quick one, if it's a quick one. Okay, then we go for a quick one in the front.
Thank you. It's Jakub again from Polish Academy of Sciences. So my question is, how much you've analyzed the residue in terms of metals? I'm interested what else you found except for iron, titanium, except for these main metals, and I mean those that do not derive from any contamination. It was pointed before that some of them are sometimes from contamination. So if you could say a few words about this.
Yeah, sure thing. So we haven't finished this work to start with that, so it's ongoing at the moment. But we're really seeing the same kind of alloy groupings that Timon presented earlier as well. So some specific metals seem to have like an affinity for grouping together in alloys compared to other ones. We're seeing as well that the residual oxygen seems to always kind of coexist with the magnesium and also the calcium, which is useful to know in terms of separation later. But yeah, we're seeing a huge range of different alloys, even within each grouping. So if you've got, say, a aluminium, silicon, calcium alloy, there might be quite a wide spread of compositions within that grouping. So it's really a heterogeneous material. But hopefully once that work is complete, we'll have a more complete answer as well.
later. That was a great talk. Thank you.
Thanks.
Thanks, Beth. So, our next presenter is online, and it's Paul Burke from Johns Hopkins University, and his talk is entitled "Studying the Utility of Molten Regolith Electrolysis in Lunar, Martian, and Terrestrial Environments." Paul.
Great, thanks everyone. Could you start sharing the slides? Excellent. All right, so thanks for all the previous speakers, really great talks. I try to follow it up. So I'm out of the Johns Hopkins Applied Physics Lab. Co-authors also at APL as well, Carl Hibbets, who's there in person with you all, so please ask him a couple questions, and Michael Nord. So next slide. All right, so the obvious reason why we're all here, MRE, molten regolith electrolysis, and also MSE, as Beth just presented, have the potential to produce oxygen and metal alloys with in situ materials, and we're already seeing, as Beth and other speakers just presented, some analogs on Earth are already proving viable in its production of oxygen. Next slide. So why do bubbles matter in space? These bubbles will form during the MSE, MRE, water electrolysis process. Well, bubbles can really have an unexpected impact on multiple fluid processes, systems in reduced gravity environments. We've seen it again and again in various processes. We see boiling heat exchangers producing bubbles that do not attach from the heater. We see air bubbles in IV bags, heat pipes being blocked by non-condensable gas evolution. So why does all of this matter? Well, the main question is, in lunar gravity and reduced gravity, once it's to Earth's gravity, will oxygen bubbles have enough buoyancy to detach from the electrode, or is there potential to stall the electrolytic process? And the basic simplified image is down there on the right. In lower gravity, there is potential where bubbles never detach from the electrode and can start to stall the electrolytic process. Beth and her team in a previous paper found that in lunar gravity, water electrolysis can be reduced in efficiency by up to 11%. So this is the main question we're asking and attempt to answer. Next slide. So our work, we have developed some computational fluid dynamic models of a simplified electrolytic MRE, water electrolysis, and MSE process. So it is very simplified, but we believe that we can see some trends that we can extend to more practical applications. So I can go through the methodology quickly due to limited time, but we used Open Foam Solver. We simplified the experiment by using just a simple quiescent gas injection to simulate bubble growth. This is not a multi-physics model at all. We are not simulating any of the metal precipitating out, but we do test various fluid properties. So we're doing water, MSE, calcium chloride, and MRE with some Highlands regolith material properties. 3 different gravity levels, 1G, Martian gravity, and lunar gravity. 2 different orientations of the electrode, horizontal and vertical. You can see those on the right. And various material roughnesses of that electrode. Next slide. This is, again, just some of the methodology of the CFD models. We are running a isothermal incompressible multi-phase solver across multiple cores. And to give a general sense of scale, it's a fairly small, about 10 by 15 centimeter fluid chamber we're modeling. Next slide. So the real variation and the real study that we really want to compare is how these physical properties vary between the different electrolytic processes. So we did water, MRE, and MSE simulations. The major contributing differences are obviously working temperature, surface tension, density, and viscosity between the three. Next. So these are some just sample results from MSE, leftmost, MRE in the middle, and water electrolysis on the right. So we find that water and MSE, when scaling from 1G down to the lunar gravity regime, the time to bubble detachment increases by just over 4x. In MRE compared, when scaled from 1G to lunar gravity, the time to bubble detachment and the bubble volume at detachment increases by almost 3 times. And the bubble sizes tend to increase when the electrode is in the vertical orientation. So that would be the water electrode on the right there. And we find that in the vertical orientation, the bubble tends to spread along the surface of the electrode, which increases the contact area, which then also increases the attraction force, or that surface tension force that prevents bubble detachment. And I'll get a bit more into the impacts of that in a couple slides. Next. So we also see some interesting behavior when scaling across gravity regimes. We're starting to see, just graphing the results at 1G, Martian gravity, and lunar gravity, we see a nonlinear power law trend when scaling across gravity levels. And we also see that MSE and water electrolysis are most similar. They have fairly similar fluid properties, which makes sense why the bubble detachment times would be similar. But all of the models indicate that there is a nonlinear scaling law from 1G down into the reduced gravity regime. Next. So I also mentioned that we tested various surface roughnesses of the electrode. And this is for water. I'll have MSE and MRE in the upcoming slides. But we find that with increased roughness, the time to bubble detachment and the volume of the bubble at detachment increase. And that is due to the fact that for rougher electrodes, the bubbles tend to spread out along the electrode wider and wider. And again, similar to the orientation of the electrode, when the bubble spreads out along the electrode, it makes greater contact area, and it increases that contact diameter of the bubble, and thus increases the traction force between the 3-point line of the gas, liquid, and solid, and prevents early bubble detachment. Next. So this is MSE, and then next one is MRE. And just to note that MRE, the roughest electrodes modeled by just the contact angle did not detach at the current level of modeling we are doing. We're trying to get better computational resources to extend those models out even further. But just to say, in MRE, very rough surface very rough electrodes greatly prevent bubble detachment. All right, next slide. So what can we glean from all of this? What can we really use from these results to influence more practical either design or further experiments to learn more about the MRE process in reduced gravity environments? So first we see that orientation of the electrode does matter. In the vertical electrode orientation, bubbles spread along the surface and increasing that contact area and can prevent and delay bubble detachment. It is important to note that this model is simplified. It uses a single bubble nucleation site with multiple nucleation sites. This may actually be advantageous where the spreading of the electrode could detach other bubbles above it. So something to note. We also see that MRE is less dependent upon gravity level when compared to water electrolysis or MSE. And we see that MRE especially is significantly dependent upon the surface properties of the electrode, and specifically surface roughness. But for very rough electrodes, bubbles in MRE, in molten regolith, they have a great deal of detachment delayment. Next slide. So is MRE feasible? We can't answer that for sure right now, but a couple important points to consider. Bubbles in MRE are much less likely to detach, especially in lunar gravity. That's because of increases in surface tension, very high surface tension of molten regolith, very high viscosity of molten regolith. As mentioned in the previous slide, orientation does matter, and when designing MRE systems that are actually supposed to operate on a mass scale, it is an important design consideration to orient the electrode in a way that will encourage bubble detachment. There is potential to stall the electrolytic process and decrease its efficiency. We do not believe it would be catastrophic. We expect to see a bit of decrease in efficiency when scaling down into the reduced gravity regime, but we do not expect to see complete stalling. But the good news is that there also appears to be methods to induce bubble detachment. And if we go on to the next slide, that's some of the future work that we may want to look at. So we'll start to model multiple nucleation sites. We've already started that, where bubble-to-bubble interactions may encourage early bubble detachment. And then other things, potential mitigation techniques such as crossflow, coatings to affect the surface finishes, and additional angles and orientations of the electrodes. But it's also important to note that while there may be ways to induce bubble detachment, the inevitable use of these systems in the lunar environment is a very harsh environment, very high temperature. The electrodes could be degraded, and no matter how many coatings or surface finishes that you put on them, these electrodes will degrade, will start to be rougher and rougher, and lifetime of these systems is another important note to consider. All right, next. All right, so this was sponsored by the Lunar Surface Innovation Initiative, headed by APL. And next, I think that's it. Excellent. Thank you all.
Thank you, Paul. I was told we don't take questions, we don't do the Q&A for the online presentation, so please use the chat function to talk to Paul. And we also, slightly behind the schedule, we have one talk left, and this is Samuel Hollows from the UK branch of Thales Alenia, and he's actually going to talk about taking the lab to the moon, and its title is the ISRU DM mission.
Yep, thank you, folks. I'm a mechanical engineer by training at Thales Alenia Space, and as mentioned, I'm here to talk to you today about the ISRU demonstration mission. So at Thales Alenia Space, one of our key strategic focuses is on in-space resources, and of course, metal and oxygen extraction falls under that umbrella. And personally, I've placed a great focus on the demonstration mission, which is what I'll talk to you about today. Over the past few days, we've talked, or we've heard some insights about the ESA roadmap to operate a lunar-based pilot plant, and the demonstration mission is one of the critical components of that strategy. So I'll explore that. Secondly, I'll discuss some of the key outputs and achievements of the work to date, and then I'll end with a note on our outlook and the next phase of the demonstration mission. So, as I said, the demonstration mission is one of the 5 critical pillars on the ESA roadmap. And the overall objective is to demonstrate oxygen extraction on the lunar surface at a significant scale. But what do we mean by significant? So we have to ensure that as we increase the size and scale up to a potential pilot plant, that the critical technologies and the design is suitably mature so that the technology is still valid. That scale, we think, is about 50 to 100 grams of oxygen, and we'll generate that during the course of a single lunar day. It doesn't sound like very much, but it's about 80 liters at standard pressure, and about enough to sustain an astronaut for 4 hours. So the architecture, it's a lander-mounted payload. We can see on the image on the right, there's a robotic arm which scoops up regolith from the vicinity of a lander and places it on top of a payload, which houses some of the pre-processing, instrumentation analysis, and the reduction reactor itself. On the left-hand side, we can see the overall development roadmap. So it started out as some initial studies and then a challenge phase, resulting in the phase B1 study, primed by Thales Alenia and supported by our industry partners at AVS, Metallysis, the Open University, and Redwire. We're just commencing our technology developments, so it's been primarily paper-based up to now, and we're going to begin an extensive breadboarding phase. And then after that, starting from about 2026, we'll proceed with a normal phase B2 CD procurement activity, hopefully targeting a flight mission towards 2028. Okay. So from the phase B1 study, there's a few pertinent outcomes which I'd like to share. Firstly, we've generated a extensive performance model detailing the full functions from the regolith collection through to the sample handling and the pre-processing, through to the disposal of a spent regolith after the reduction reaction. I don't know if this video will play, maybe not. Maybe we can play the video in figure 3.1. But what was the purpose of this performance model? It helps us to verify the design. We can perform various trade-offs and perform virtual experiments. It helps with visualization of the payload dynamics. So in figure 3.1, which you can't visualize at the moment, but we were able to see the concentration of the calcium oxide, which is one of the active ingredients in the reduction reaction, and it's diffusing and its concentration fluctuating throughout the course of the experiment. One of the other key outcomes was the maturation of a modular approach to the payload. So in addition to the normal benefits that a modular approach brings about, such as a simplification of the interfaces and integration, it also means that we can maintain a very good degree of flexibility to alternative mission and lander architectures. For example, we're able to split the payload into multiple zones to to allow us to interface better with various volume envelopes and also help with mass balancing considerations on smaller landers. It also enables us to pick and choose some of the hardware and functional elements which we want to take so that we can comply with the overall mission constraints such as overall payload mass, the concept of operations, or the mission objectives. And finally, it provides us with a really good resilience to some of the inherent uncertainty and low technology readiness levels of some of this equipment. So we're able to pick and choose the technology as it matures. And that's exactly what we intend to do over the next phase, is develop the technology and reduce the uncertainty. So what uncertainties are there? Firstly, there's uncertainty associated with the mission architecture, which I've alluded to. The other is related to some of the critical technologies that are at low TRL. So there's an example on the slide of resettable seals, but you can find examples throughout the whole payload from some of the mechanisms through to the instruments. And finally, there are uncertainties associated with a specific process performance, which Paul very well detailed the bubbling aspects, so I won't go into too much detail on that, but I will draw attention to the great visualization within the video, which is not playing, but I'd encourage you to check some of the work performed by the team at ESA in making those videos. Of course, we have our extensive performance model, which goes to remove some of these uncertainties, but there are data gaps which we need to fill. And that's the objective of the next phase. I don't think we found batteries for this one, did we, from yesterday? Can we go to the next slide, please? So the next phase, with updates, will be an extensive test phase. As part of our test plan, we will have a tiered approach, so 3 phases. In phase 1, we'll perform piecewise or coupon level testing, hoping to increase the TRL up to 3 or 4. And within that phase, we'll have 3 parallel hardware streams. So the first concerns the sample handling, which is responsible for the movement and flow of regolith through the payload. The second branch is for pre-processing, which will turn our raw regolith into a good feedstock suitable for the reduction reaction. And finally, we have the crucible in process, which performs the reduction reaction itself. The next phase, which is aptly named phase 2, we'll create a breadboard at subsystem level. So integrating these various equipment parts, targeting a TRL of 4 or 5. Hey, there we go. So yeah, phase 1 at the top with the 3 parallel branches into phase 2. And then for phase 3, we bring all of these various, the 3 subsystems together into an integrated breadboard with the hope of achieving TRL 5 or 6. Just a quick note, in my mind, it's very easy to think of breadboarding as an activity that you perform on in a couple of spare hours with scraps lying around a workshop. But the extent of this breadboarding is very extreme, so we want to demonstrate the full end-to-end functionality of a payload. And that includes over 90 unique tests and test setups. Do I dare press onto the next slide? Yes. OK. So to quickly summarize, I realize we're in lunch, and I've grown quite fond of a cake. But we have a large design envelope. We have some knowledge gaps, and we want to perform an extensive test regime to better understand these ideas. And from that, we can work within our large design envelope onto a single consolidated design, as per your normal engineering development for a space program. And then finally, in 2028, we will demonstrate oxygen extraction, about 100 grams on the lunar surface. So again, thank you for listening. It's been quite a short talk, but I'd encourage you to check the references for further reading. Otherwise, you can reach out directly now or after the talk to myself or any of the collaborators at ESA, AVS, Open University, Redwire, or Metalysis. But thank you for listening.
Thank you, Sam. Sorry for these small technical problems. Other questions? I think it's been a long session. We are all ready for the lunch break. Okay, then I would suggest we extend this into the lunch break and you just catch up with Sam to talk to him about the DM mission. Okay, let's thank the speakers all again.
You can hear me. Thank you for those still online. We are going to have a lunch break, and don't worry, it's going to be extended until 1:40. And I've been asked to remind you that you can still vote for posters in the competition until the end of the lunch break. So please take your lunch around the posters. Thank you. See you at 1:40.